Hello, this video is for Winter, the Phi-minster. If you are not Phi-meister, if you are not the Phi-meister and you are watching this video, consider yourself. So the first thing we want to go over is vectors. They're just like numbers. They're algebraic, mathematical objects made of numbers. They just have some special operations and things that define them that we don't actually have to get into for the most part for this problem set, as far as I know. So we're just going to do some basic vector geometry type stuff. A vector is a collection of some number of numbers, some dimensionality of numbers. Typically we think of them as two-dimensional vectors because we're usually working in two-dimensional planes. It's very convenient. So one might be like a vector 1, 2. And if we were to put that on our Cartesian plane, that might look like, starting at the origin, something that goes 1 over, that's the x, and then 2 up, that's the y. And importantly, it has a direction. So a vector that's pointing up is not the same as a vector that's pointing down. There's kind of a different way to represent that than just by two numbers conventionally, sort of. But we're not going to worry about that so much, because what I want you to know how to do, know what vectors are. Oh, and then some other parts, they have a magnitude. A magnitude is just the length of the vector. So if we do a more convenient vector, perhaps the vector 3, 4, very astute listeners might already know the magnitude of this vector. I did very badly in trigonometry, but I got better. This is 5. It's a 3, 4, 5 triangle, very common, like fundamental triangle. And so you might then notice that to get the magnitude of any vector, we just square its components. So if this is vector v, which we can denote like that with the little arrow above it, on the top of a little hat, the magnitude of vector v, which we write kind of like the absolute, kind of looks like the absolute value of vector v, is just x squared plus vector y squared square root. That's the magnitude. You'll need that, kind of. And then the other thing that a vector has is an x component and a y component. I just erased it, but I'm going to draw that vector again because it's helpful for this. So the same 3, 4, 5 vector, 3, 4, 5, it has in the x direction kind of like a subvector, if you will, of something that's just 3, magnitude 3. And so we could actually, if our whole vector is 3, 4, we could break it up into some vector with 3, 0, which would be this right here, and then some other vector of 0, 4, which would be that. You could center it on the origin. Where it's centered in this case doesn't really matter, because we're just doing them as coordinate points. So it's as tuples. So it's assumed that they're centered on the origin. But you add these together, you get your 3, 4. Again, you might also remember from trigonometry that we can take the magnitude, or we can take the length of some triangle times the sine or the cosine of an angle to get the kind of the height or the length, if you will, the width of that triangle. You will also want to keep that in mind. So that's basically, is that the found? I have notes here about what I wanted to talk about. Oh, the other thing is dipoles. I'm pretty sure you remember this, but we'll go really, really quick. For some molecule, let's assume we have like HF. As you know, hydrogen, super loose with its electrons, fluorine not so much, very picky, very clingy. And so this would be a pretty strong dipole. I mean, that's probably ionic, right? But let's not even think about that. And we would represent that with this partial negative charge, because this fluorine is going to pull more electrons, and this hydrogen is going to have a partial positive because it's having its electrons taken away. We can represent this with a vector that points towards fluorine, the more electronegative one. You could have it going the other way, but this is convention. This will also be important. So what the question is asking on the problem set, it's asking about water, H2O. So let's draw that. Your H2O, very lovely. And it gives you some important information. It gives you different angles of these bonds, and then it also gives you the magnitude of the kind of the pull. Only for hydrogen, it only gives you that dipole moment, if you will, for hydrogen. And the dipole moment, again, is just, I didn't explicitly say it earlier, it is the vector that points to, the more electronegative one, the thing that's going to have more electrons and a more negative charge. So what the question is asking for is the net dipole moment of this molecule, which just means we add up all of the dipole moments that compose it. And if we center kind of our origin at oxygen, we don't have to worry about whatever oxygen does, just the ones that are contributing to it. Very convenient. So then this last part here about determining this net dipole moment is we just want to sum up these vectors. You can sum vectors, if you want to think about it geometrically, as just kind of adding them from tip to tail. So I will try to kind of draw these to scale. We'll start with this vector here. If I put it on the origin, maybe it goes out that distance, and then this other vector, if we add it here, we would start it at the end of this vector and then just draw it. And then the end result, the vector sum, the sum of those vectors, is just whatever new vector that we get by going from the origin to the point that we end at. So here we get a vector that just goes straight up. You can also think of it mathematically as just adding them by their x components and their y components, or their z components if it's three-dimensional, et cetera, et cetera. The cool thing that's going on here, which makes this problem a lot easier, is that this molecule, being a molecule, is completely symmetric. So whenever we think about the x and the y components, and because those are vectors, the x components are going in the opposite direction, and they're of the same length because it's symmetric. And so whenever we add those together, it goes out one distance, and then it comes straight back in that same distance. That has no net effect. That's zero. The y components, there's two of them. They're also the same length. And so that's basically just one y component doubled. And so whenever you're calculating this, and I think I have it, you'll be able to see it in my notes, you just find the y component that's kind of the dipole moment of just one of the hydrogens. So you do some trigonometry with this, which is what you're given. You multiply that by 2, that's your net dipole moment for the molecule. Very convenient, very great. That should be that first problem. And then our second problem, how long is this video? Ooh, a little long. I'll be quick. This one's really just algebra and trying to give you an idea of what kind of the physical reality of the quantum mechanics simply is going on. So this one's talking about gerade and ungerade orbitals, which is just like German for symmetric, basically, or inversion symmetry. And so the physical reality that the math is describing of quantum mechanics can even be said to have such a thing are orbitals where there's kind of like a positive and a negative lobe, and then one where, and I might be getting this wrong, check your notes, there's kind of just one lobe. Maybe don't believe me on that part. I need to actually check that. But it's just describing different orbitals. To actually do this one, and of course you'll be able to see it in my notes, but kind of the basic gist, we have two different wave functions. We have the, let me try to actually draw psi here. We have psi, sigma psi, gerade, and then sigma psi ungerade with the u. Whenever you look at them, the only actual difference between those two wave functions is there's a negative sign right, let me see if I can point it out here. The negative sign is right there, between the e terms. One of them is positive, one of them is negative. Everywhere else the algebra is the same. So that kind of makes writing out the proof of the algebra a bit easier, which is like half of what this problem wants you to do. To actually do that, to actually do the algebra, you just start with what you're given, and you'll be able to see it on my notes, but it's the n sigma times, what was it, I think, yeah, psi a given r, that's a vector, sorry about the a, that's also an r, sorry about the r, plus yada yada yada. You just start replacing each of these terms with what they're equivalent to. So we know that n sigma, in this case, is like n sigma over root pi. We know that psi a given r is equal to, I think it's, yeah, e to the negative, and then this is a magnitude, or I think it's absolute value magnitude, kind of the same thing here. This r, that's an r vector, minus a, the a vector. And then we know that this is equal to kind of do some of the algebra so it doesn't stump you, e to the negative, I think it's z plus 0.07. Basically, you're just kind of following the algebra that it gives you in the book. You're just making substitutions, and then eventually you get to the thing it wants you to prove by doing some more algebra. Mostly substitutions. And then the other part is graphing it. I just used Desmos because I love Desmos. And then I used that to get the points and understand the wave functions. You should get something, unless I did something horribly wrong, that looks like this. Um, I believe the blue one is Garada, the red one is Ungarada. You can see what's going on here. I could have that mixed up. I'm just kind of looking at it. Now, actually, let's see. Yeah, blue is Garada, red is Ungarada. You can also find it in the book. They mentioned the Oxtoby chapters. You can find it in, if you want to check there. Um, let's see. Oh, and then one quick thing that I forgot to mention for the first problem, the second part where it's asking about how your dipole moment compares to the published one. The published one is for water in the gas phase, which means that it has a lot less intermolecular force with the other water molecules. It's bouncing around a lot more because it's in the gas phase. That's how we define a gas. The molecules are much more loosely associated. Whereas in the liquid phase, they're still kind of sticking together. So I may not be correct. I double checked my math. I'm not super confident. I got like 4.6998 Dalton, or I forget the units, D, 4.6998 D. The published value is like 1.9 or 1.5, I think. The book gives it to you, or the problem set gives it to you. But the important thing is that about 4 times kind of makes sense because ours is representing, or the value that we find is representing water in a much more solid phase than the gas phase. So don't feel like you're super wrong, but do check your math. I think that's it. I think that's the main thing. I'm looking at it now. I might have to reverse my final net dipole moment because I drew everything going to the hydrogens. Again, double check that, find out which way it's supposed to point for sure, but the vector math is basically the same. You're just switching whether it's up or down at the end if I'm wrong there. Yeah, that's the main thing. Let me know if there's more. I may not be able to make videos for the other problems, but I can still just send you my notes. All right, bye.